Hello guys, welcome to the Math Show. And what a pleasure guys having you here on my show. Today we're going to be talking about complex analysis. What is complex analysis? You may say. Basically, complex analysis is the study of the complex numbers and their properties, as well as the algebraic structures and analytical properties as well, which deals with limits and continuity and derivatives and integral and much more. Complex number is the field of mathematics that deals with a space in which you have the real numbers and the imaginary numbers are connected in such a way that it kind of bridges the two branches of mathematics together. And it's such a remarkable and beautiful way. Well, complex analysis pretty much formed around about 1800s, and some of the major contributors, Cauchy, Euler definitely made a big impact on that type of mathematics. Cauchy has to do with the idea of limits, so we can thank Cauchy for his study of limits, right? Such as brilliant French mathematician. Well, Euler, however, he produced lots of mathematics. We got about 9 to 10 volumes of his work, and some of the stuff which we're still trying to figure out today. So I learned this from my former professor by the name of Art Costello. Very great gentleman, by the way. So one of the ideas of complex analysis is basically, well, we're going to solve a certain problem, right? In terms of its solutions. And what the solution is derived from the equation x squared plus 1 equals 0, which has stunned mathematicians for hundreds of years. But it's until the 1800s that was resolved by a few mathematicians. Well, prior to that, complex analysis were regarded as ghost numbers, hence the word imaginary. They didn't really play a pivotal role in mathematics, because mathematics was evolved, at the time around the real numbers. Okay, so and it still took its shape until the 1900s, really 1900s, 1800s, and that was during the development of Einstein's theory of relativity and quantum mechanics. Those are two dominant fields. Okay, so Planck has a major role in the quantum physics, as well as Schrodinger probability theory, which is this famous equation which contributes to the probability of where the particle is located. Okay, it gives you that probability. So anyways, so complex analysis also play a pivotal role in terms of rotation, right? So you have a spin, and that was dictating that spin, for example, is the complex number. So it's the number which defines it is I equals to square root of -1. And that's the basis of all our study of the complex numbers. You have what they call the z, right? Z is the complex number, which is a plus bi. It also helps construct certain functions and all that stuff. So that's one of our base numbers. And what we do when we add complex numbers, you add the real numbers first, then you add the imaginary points second. So it'll be a comma b, right, represented as a vectorial form, which is pretty cool, because when you add the complex numbers, you're also adding the angles, which led by such a beautiful result of Euler, which is e raised to I times theta equals, we call it W. So that'll give you a solution to the equation, right? And which also played a major role of the fundamental theorem of algebra. Let's talk about that. So the fundamental theorem of algebra tells us that you at least have one complex solution. You could have more. And that's very important in terms of solving polynomial equations in terms of z instead of x. So whenever you have x, let's replace it with a z to get your complex numbers. So for example, let's say you have x squared plus 1, we get plus or minus I, or the absolute value x equals I. And from there, we'll build an algebraic structure around there. those numbers. So we come up with the addition law, division, multiplication. All those, actually, addition and multiplication are closed under the complex number. Okay, those are closure properties where you can add and multiply. And from there we can derive other properties like the distributive law and all that stuff, which still holds up in the complex as well. So let's take another example. As you multiply a number times itself, like I times I, you get a very interesting result. So you get I squared equals what? -1. It's kind of like you square both sides. Now that's kind of strange. Well, I to the square, what does that mean? So remember we agreed on the original definition, I equals root of -1. And you take the square of both sides, right? That's a number. You get back to a negative. You get a result of -1 once you square. And we also have projections, and we have curved linear spaces as well. We use another different dynamic, which is some elements of vector analysis. So that'll be integral loop f of z times d of z, right, with respect. So we have f of z of t with respect to dt, right? That'll be your formula, and that'll give you a path in the complex field. Remember that path can be traced out with a function, and that's why we named it that way, right? So we will be exploring those later on in our lecture and stuff like that. So I hope you guys have a good feel of the complex numbers. And guys, thank you for watching. We hope to see you in the next video. Bye-bye.